Hello, dear participants of the RSS workshop on differential geometry. I'm Alin Albu-Schäffer, and I will talk today about the geometry of nonlinear oscillation modes in robotics and their application to locomotion and manipulation. It is well known from biology, and in particular from biomechanics and neuroscience, that resonance effects based on the elasticity of muscles and tendons play a crucial role for energy efficient and high performance locomotion. So it makes sense to think implementing such effects also in our robotic systems. However, today we are largely missing the tools to describe, model, and control nonlinear oscillations of multi-body complex systems, which are far away from the linear operation regime we are used to in engineering. And based on this idea, I proposed a European research grant project, which, as I'm working at the German Aerospace Center, focuses on an application in a planetary exploration context. For example, imagine landing on a planet, for example, on Mars. You need to still today land in flat areas, and then you would like to travel to some canyons or gorges in order to look for geologically interesting sites. So this was my primarily motivation for efficient locomotion. And the inspiration was, as mentioned, taken from biology. Probably most of you know this plot, which compares cost of transport to locomotion efficiency of different species. And several robotic groups placed their dots for their robotic systems there as well. And apart from very specialized locomotion systems like the Cornell robot, for example, most of the robots are by almost one order of magnitude less energy efficient than biology. Why is that? Well, there are plenty of experiments in biomechanics which show that animals, of course, they display different gaits, but they would adjust or choose their gait according to the locomotion velocity in such a way that they maximize their energy efficiency, so they minimize the cost of transport. And there is a beautiful work of David Remy and his co-workers who simulated a purely passive model of a quadruped system. Of course, it's simplified because it takes some assumptions of zero loss at the impact with the ground, but they have shown that basically just giving an initial condition, appropriate initial conditions to the system, you can recover by optimization process all the standard gaits of, for example, horses like walking, tilting, galloping, bounding, and so on. So this is very exciting because this confirms that indeed most of the gaits can be expected to be embodied in the mechanical properties of the systems themselves. However, our engineering intuition tells us that coupled multi-body systems in complex potential fields tend to be rather chaotic. So the question I'm looking at in my project is looking at a biomechanical system with bones, muscles, and tendons, which we replicate in robotics, of course, by links, rigid links, then actuators, and then springs, and maybe dampers. We would like to search for periodic motion of these highly nonlinear systems. And it turns out that the most appropriate tool to generalize from the linear case to the nonlinear case as so often is differential geometry. First of all, let us start with our dynamic equation for robots, which we most often employ in written in the notation above here, which I divided by the inertia tensor. So basically, we write this dynamic equation on the level of accelerations. It reads joint acceleration plus m-1 times the Coriolis and centrifugal terms equals to the acceleration due to the potential field plus some possible input acceleration coming from the motors. Well, in differential geometry notation, this reads covariant derivative of velocity with respect to velocity equals to minus the gradient of the potential u and plus some input acceleration. Now consider mechanical system, which is described by the Lagrangian function, which is the difference between the kinetic and potential energy. From the principle of least action, we know that the motion of the system will be such that you extremise between 2 points the integral of the Lagrangian. So you extremise this cos function, which is given the Lagrangian. Now, in the case that we have a system of pure inertia, so no potential function, then this reduces on extremising the arc length between the 2 points. And this means computing basically the arc length integral with respect to the inertia metric tensor. Which means that the principle of least action just tells us that trajectories of a freely moving multi-body system are geodesics with respect to the inertia metric tensor in the configuration space Q. Actually, you can show this analogy even more by finding a manifold which really embeds this metric. This is what I have done here. I sliced up the torus, and this video shows that basically there's a one-to-one relationship between the dynamics of a double pendulum and the dynamics of a pure point mass moving on an appropriate Riemannian manifold, which is characterized by the inertia tensor asymmetric. Well, what is the situation if we add a potential field? So if we have a conservative dynamical system described by inertias and by a potential field in the notation we said before, actually one can show that in this case, the trajectories of a conservative mechanical systems are again geodesics, but now with respect to another metric, which is the Jacobi metric tensor in the configuration space. Basically extremising the length integral with respect to a metric tensor Gj, the Jacobi metric tensor, which is defined as follows, is the inertia metric tensor Gm times 2E minus the potential function. E is the energy of the system, which, as we considered the system to be conservative, is constant. This has some important implications because basically we reduce the search for example, of periodic trajectories of a robotic system to a search of geodesics on Riemannian manifolds. So basically, robot dynamics generally reduces to the motion of a point on a high-dimensional manifold. And this implies that we can use a lot of tools from topology and Riemannian geometry to study the motion of dynamical systems. And I will give you some examples. Basically, the analogy we described before means that searching for periodic trajectories of robots is equivalent to searching for closed geodesics on manifolds. And closed geodesic on manifolds is a very classical question of differential geometry and topology since more than a century. There are plenty of results in theoretical mechanics and mathematics related to this. Just a very classical example tells us that having a double pendulum, so a robot with 2 degrees of freedom, then for any 2 integers m and n, there will always exist at least one periodic motion of a double pendulum under which one of the segments makes m rotations while the other segment makes n rotations. How can you prove that? Intuitively, it's very simple. Because we know that trajectories of the double pendulum are geodesics on the 2-dimensional torus, just imagine taking a rubber band and wrapping it n times around the one dimension of the torus and m times around the other dimension, then gluing together the ends of the rubber band and letting that contract without friction on the surface of this torus. It always will converge to a minimum length. This minimum length is geodesic. And this geodesic is a trajectory on dynamical systems. And this will happen for every pair m and n of integer numbers. Now you can have different types of periodic trajectories. And if we want trajectories which are a one-dimensional manifold, then there are only 2 topologies of one-dimensional manifolds. Either it is a line segment or it is equivalent to a circle. And the examples I presented before, they are closed trajectories. So they have a circle topology. While in most of the cases, when we look at oscillations, for example, of a biological or a robotic limb, they are not endless turning joints. So rather we look at geodesics with line segment topology. And this kind of trajectories have been named braking trajectories in differential geometry or in Hamiltonian mechanics. Let me give you some details about how braking trajectories are defined. They are included in a volume bounded by the equipotential surface. So we talk again still about conservative systems. And because these trajectories have a line topology, they have to retrace themselves. So they are rest-to-rest motions, and that's why they are called braking trajectories. There are some major results since, well, the middle of the last century, actually. And the first very relevant paper regarding braking trajectories has been written by Seifert, and he has proven that for every classical conservative mechanical system with closed and bounded maximum equipotential surface exists at least one such braking trajectory, which is an interesting proof. So for every robot satisfying this condition, we know that we have at least one such periodic trajectory. And actually, Seifert also stated a conjecture saying that as in the linear case, you can expect for an n degree of freedom system as above, that you have at least n braking trajectories. Proving this conjecture is still the topic of current research. It is proven for more and more general cases, but I think there's no proof which would apply also to all robotic systems as far as I know. Now, let us see how we can define the generalization of normal modes and how we can start from the linear case and extend the definition to the nonlinear case. To this, let us first look at a linear case example, of course. Consider a set of point masses connected by linear springs. Then the dynamics is described by a set of linear differential equations. And of course, we can solve this linear set of differential equations. And we know that we have some special directions which are given by the eigenvectors of the system of equation, such that if we initialize the motion along those eigenvectors in configuration space, then the system will always stay on those eigenvectors. Stated differently, if we look at the time evolution of motions which are initialized along the eigenvectors, then we know that all solutions are similar in the sense that they will always pass through zero velocity. At the same time, they will have their maximum peak at the same time. Basically, each individual coordinate is just a multiple of all the other solutions. And this is valid for any energies. Now, it was known also in mechanical engineering since the 60s due to a very nice work of Rosenberg, that this is the case also for some particular nonlinear systems. So for example, if you take a similar set of masses as springs, but having cubic springs, again, due to some symmetry properties, you will have again a straight line in configuration space, which is invariance. And this is what Rosenberg called similar normal modes. However, the effect of having a line which is invariant is a very particular case in the nonlinear situation. Why? Because this is, as we will understand, this is related to the notion of geodesics. If we are in the linear case, then the mass matrix is of course constant, and shortest distances between points in configuration space are straight lines, as we of course know. Now, if we want to generalize this to multi-body systems, then we have a variable configuration dependent inertia tensor. And the distance between points is depending on the path, as we discussed before. And then you might also have springs which are nonlinear due to several reasons. So basically, we have to move from Euclidean space to a Riemannian case to describe those systems in Riemannian geometry. The fact that geodesics are straight lines in Euclidean spaces but are curves in Riemannian manifolds, makes us thinking about generalizing the notion of a normal mode on Riemannian manifold as being a curve which is invariant no matter what the initial velocity of the system is, as long as the initial velocity is tangent to that curve. So we could ask the question, is it possible for a robotic system or for a multi-body system with potential fields to find such curves which are invariant no matter what the level of the energy is if initiated with a velocity along that curves? And this is what we published this year in Robotics and Automation Letters together with Dominic Lakatos and Stefanos Ramigioli. And we have proven that a necessary and sufficient condition that you can find a curve which is invariant no matter what the energy level with respect to the dynamics of the system is that this curve is a geodesic with respect to the inertia tensor, and the acceleration due to the potential field of the curve is tangent to the curve. And here you see this condition visualized. So basically the covariant derivative and the gradient of the potential, they both need to be tangent. This is a necessary and sufficient condition. And in the paper, we gave some simple example for a double pendulum where we show that you can take any geodesic of the system without potential field. So basically you just simulate the system without potentials, just a multi-body dynamics. Take any of those trajectories and then you can shape the potential field in such a way that any of these trajectories becomes what we call strict nonlinear normal mode, so becomes invariant in such a way that if you initiate it, then the oscillation will happen along that curve no matter what the amplitude, and you can even design the potential in such a way that when moving to the side from this curve, the potential will increase such that this curve will be attractive. And the mode will be then also attractive in a neighborhood of this curve. And this is just one very simple example showing a strict nonlinear normal mode. Basically, the theorem does not require the potential to be positive, definite, or smooth. So modeling the ground interaction as very stiff compliance allows to directly apply the strict mode theorem to show that such a hopping motion of a symmetric quadruped is indeed a periodic trajectory on the mode. This is the good news. The bad news, however, is that if you take a potential field which is not tuned to the inertia properties of the system, you cannot expect such a curve to be invariant no matter what the energy level of the system is. By changing the energy level, you will find another curve which has these invariance properties. So these periodic trajectories are in the general case energy dependent, and the mode splits into a bundle for various initial velocities or energies. This again was defined in the overview paper of Rosenberg in the 66, and that's why we call this kind of modes, which are energy dependent, Rosenberg modes. I will give you an example again for the double pendulum. Let's consider a double pendulum with just a quadratic joint level potential field, so just linear springs in the joints. And then by doing some numerical optimization, you can search for the periodic trajectories for the braking orbits. And what we have seen is that indeed you can always find at least two such trajectories. And what we display here in magenta and yellow are the modes of the linearized system first. Of course, you have two modes for 2 degrees of freedom system. And we see that for increasing the energy level, you continuously find those two modes. And one of these modes in this particular case happens to be what we call the strict mode. So basically you have a line, and when you increase the amplitude, the oscillation will always happen along that line. While the other linear mode evolves into something what we called here a Rosenberg mode. So for a while, the linearization still holds, but when the energy becomes bigger and bigger, this trajectory starts bending more and more. Again, imagine that what we are talking about is a curve on a piece of the torus, and the system will always evolve for a given energy along this curve, as in this image. Here you see how the two modes look like. Actually, you have a in-phase mode where both joints oscillate with velocity having the same phase, and an anti-phase mode in which the joints have mostly opposite side. And here you see a lot of trajectories having as initial point this red asterisk, which is a point on the boundary of the maximum equipotential lines. You see that most of trajectories are quasi-periodic. Sometimes we have some complicated periodic motions, but here you see the first mode, which is the antiphase mode. And later on, you see when the initial condition gets to the right point, you will have another mode over here, which is the in-phase mode. And there is also some continuity with respect to the initial conditions. Okay, so this is about Rosenberg modes. What about adding damping to the system? So far, we only talked about conservative systems. Now, when you start adding damping, of course, in the one-dimensional case, you know that instead of having an invariant line, you will have an invariant plane in the phase space. So the line was in configuration space. For adding damping, you need to consider also, to represent also in a space including the velocities. So the phase space, which is a space of configurations and velocities. And now you will have an invariant plane in which, for a modal oscillation, the motion will spiral down to the origin. Now, again, you cannot expect in the nonlinear case to have planes, but you can expect to have a curved manifold. And actually, there's a work by Shaw and Pierre who defined nonlinear modes as being invariant manifolds in phase space. And together with Cosimo della Santina, we published a paper in ICRA 19 looking at simplified models of legs and taking this definition of modes, which again, I won't detail further, but we see that also for this kind of system, you see periodic motions now and then. You see quasi-periodic motions, but in this case, also the system in between becomes quite chaotic. So we see that nonlinear systems can have a very rich behavior ranging from chaotic motion to quasi-periodic, and then also again to modal oscillations. Here you see again one of the modes, a second mode, and in between chaotic behavior. Let us summarize the results so far, and I would recommend, if you are interested, to look at our publication of Cosimo and myself in the annual review and control, where we try to summarize and bring a little bit of structure in all possible definitions of modes we could find in different areas of mathematics, physics, and engineering. And they all try somehow to generalize the notion of the linear eigenmode for more and more complex systems. And depending on how many properties you would like to retain of the linear mode, you have different definitions. I introduced the Rosenberg mode, where the straight line bends in a curve, which passes through the origin and is monotonic. I very shortly touched the Shaw and Pierre mode, which breaks down to an invariant two-dimensional manifold in phase space. I won't go more into detail for that, but look at the review paper. Then what we call it standard Rosenberg modes, because we cannot really expect to have Rosenberg modes for robotic systems. This is what we found out. But the periodic motions for robotic systems are actually non-monotonic. And that's what we call expanded Rosenberg modes. And then at the other end of the story, we have the differential geometry concepts of braking trajectories, which can be very complicated motions. And even the more general case of general oscillations. So for example, also closed orbits, not only orbits with line topology. And it turned out that what we are interested in robotics to best describe the periodic trajectories we can find there by numerical simulations is something in this gap in between, and that's why we provided in our review paper our own definition of a nonlinear normal mode. Because for robotics, we need something which is a line-shaped, so one-day manifold periodic trajectory in configuration space. It is nonlinear. It is non-monotonic as the extended Rosenberg mode, but also does not in general pass through the origin. So it turned out that only for special symmetries you can expect this trajectory to pass to the origin being the equilibrium point of the potential field. But sometimes if you increase energy, the periodic trajectory will move along away from the equilibrium point and not pass, interestingly enough, through the equilibrium point. And I think this is due to the Coriolis and centrifugal terms. So this is the definition which we try to introduce. And I won't speak today about the phase space definition. Again, please look at the paper if you are interested, but only about the configuration space definition. Just to understand, as we have seen from the visualization before, there are plenty of periodic trajectories starting from this equipotential line. However, we are interested at those with line topology, so which have a relatively simple structure and which we can hope to lead to some simple and well-structured locomotion gains, for example. This is the type of periodic trajectories we are interested in as an example for the double pendulum. Now, let us give a brief intuition how we can define a mode of this type. We start from the linear mode, as we always did, and we know that the linear mode is a line passing through the equilibrium point, and the amplitude of the oscillation will increase for every energy level, but the motion will always stay on that line. Well, we cannot expect the same thing to happen in the Riemannian case because we don't have a generalized eigenvector in the Riemannian case. But instead of having the direction of the oscillation along a generalized eigenvector, so on a straight line, what we introduced here is the notion of a generator. So a generator is a curve having the property that no matter what the energy level is, the nonlinear oscillation would always have one of its two ends on this generator. And you can, design algorithms to numerically find these trajectories. And of course, for low energies, you will get closer and closer to the equilibrium point until at the linearized case, you will turn into a linear mode. And if the energy increases, the trajectories will get longer and longer and more bent, right? Of course, this definition of the generator is not unique because you could take also the other end of the trajectory and get a second generator. But basically, given the generator and the energy level, it's very easy to reconstruct the entire trajectory because you just need to simulate the dynamical system from the point corresponding to the according energy level. So the generator is the only thing you need to remember when you would like to display and analyze the oscillations for different energy levels. And this is the result, for example, for a double pendulum with a spring in the elbow and being just exposed in the potential field, so no other potential than gravity in the shoulder. And what we see, the dashed lines are the eigenvectors of the linearized system, and those modes start along the linear modes, of course, but then when energy increases, they will deviate. So these are the two generators for the two modes of the double pendulum. But interestingly enough, we see that if energy is big enough, some additional generators appear. So we will have more than only two periodic trajectories for high enough energies. And this is something which often appears. So what we learn from that is actually in the nonlinear case, you might even have much more periodic trajectories than in the linear case. These are, the plots in Cartesian space of one of those modes. I think this is the in-phase mode. And here you see the different trajectories which all emerge from this purple generator. and bend more and more for higher energies. Here you see some further examples. For example, a serial link 5 degrees of freedom manipulator. And here again, you see the in-phase mode. Of course, at the beginning, it looks quite linear, but when the energy increases, it becomes more and more nonlinear. We have some software toolbox which helps optimizing and searching for those modes. Here again, you see another mode which at the beginning looks, quite simple, but then gets more and more complex for higher energy. So to summarize, I think we have exciting times for understanding the structure of nonlinear dynamical systems, because for a long time we had only numerical optimization, Poincaré section analysis, for example, and it looked like searching for naturally structured periodic motions in multi-body elastic systems is like looking for a needle in a haystack. Now, I hope that I could convince you with this presentation that there's a lot of structure inside. There are many modes, and not only one type of modes, but various type of modes, strict modes, Rosenberg modes, our own definition of modes. So rich structure exists, and I think we are still at the beginning of this journey, and it's worthwhile exploiting theoretically this, but also using them practically. I think there's a lot of potential for increasing the performance of robotic systems based on this theory. And I will give you some examples on that. We all know the spring load inverted pendulum model, which very well describes the dynamics of most biological systems, the dynamics of the center of mass. Now we try to build robotic systems which embed the spring-loaded inverted pendulum model into a complex kinematic structure with legs with inertia and springs, and analyzed a two-segmented leg and a pantographic leg. And we published this in RAL in 2017 with Dominic Lakatos, and we could show that actually for the two-segment leg, you can have a strict mode. So you remember the one which is invariant with energy, only if the inertias of the leg are very small, actually get zero. While for the pantograph leg, there are plenty of parameters for inertia, length, and stiffness, for which you can design a strict mode. So you can design the line connecting the tip of the foot with the hip to be a strict nonlinear Normand mode. And maybe we think that is not by chance that in biology we have this pantograph structure, implemented in many of the biological legs, because of course a strict nonlinear Normand mode is a tremendous simplification in terms of dynamics. And here you see an implementation in simulation where you have a three-segment leg, which is basically a pantographic leg because it has some couplings between the joints. And in case of correct design, you have the vertical line being strict mode as desired, while if the potential is not well tuned, then you have a quasi-chaotic motion. We submitted just a paper to IROS where we indeed designed and did also some experiments with a real leg implementation where we indeed have chosen those parameters for stiffness and inertia and have shown that to a very good extent you can implement indeed a pantograph structure with a vertical strict Normand mode. What I would like to show you now is a design of a quadruped which we are just assembling right now, and where we analyze the linear modes first of all, and then also their nonlinear mode extension, which we excite by a controller I will present in a minute. And we see that those intrinsic modes are very similar to some biological motions. Just a few mentions for the type of the model. In this case, we attach the legs to the ground, so the feet are connected with ball joints to the ground, such that the overall system has only 6 degrees of freedom. So you expect to have 6 modes. And this is one of the modes. This is a second mode. And put together, here are all the modes you can expect. They are rotations and oscillations and coupled motions. And interestingly enough, if you detach the legs, for example, for this mode, back and forth oscillation, the robot starts to do some natural walking motion. The same thing for this twisting motion. When you detach the leg from the ground, this twisted mode evolves into some legged walking pattern, which is interesting, but we need to still explore further this aspect. Now, let us spend just a few minutes to the question of control. Now, assuming that you have a mechanical system which intrinsically has some nonlinear oscillations which correspond to gates you would like to have, then instead of doing the classical locomotion control and controlling at millisecond rate the trajectory or the dynamics of the system, you would just like to let the system evolve along that mode. And from time to time, with a low control rate, just re-inject the consumed energy. And this is what happens, for example, when exciting a swing. You would not like to run back and forth and control the swing at each time instant, but just inject energy. And by the way, the swing trajectory, I think it's also a strict nonlinear normal mode. And we looked at how humans do that. Humans are very skilled of injecting periodic oscillations, for example, in a rod. And if you ask people what they do, they say, you know, I just feel the force, and whenever the force exceeds a certain threshold, I give an impulse to the rod. And this is what motivated us to define a simple bang-bang controller, which on a threshold on the torque along the modal manifold commands an impulse which we implement in the form of a delta displacement of the equilibrium position. We have proven that this converges to a limit cycle in the one-dimensional case, but this works also very well in the multidimensional case. So imagine you have a mode which you even don't know precisely for your robotic system, and you start applying impulsive motions, one per trajectory, once per period, and then observe the system for the duration of a period and adjust the direction of the impulse such that the average motion corresponds to the direction of the impulse. Here again, the details you can find in this Bio publication. At the end, we could show that this converges to a periodic motion. And the way we implement is that we measure the joint torques in all joints, then do a linear transformation with a weighting matrix V, which we adjust according to the rule before, to a one-dimensional so-called modal torque. And then we apply the thresholding function and command the impulse in joint space. And then we transform back with the same linear vector V to displacements on every joint. And interestingly enough, you can implement this very simple adaptation rule by a Hebbian learning rule and, well, some additional neuroscience concepts we introduced to implement this control law with a neural network. So what we do, we measure the torques, do a linear transformation. Then when you reach a threshold, you fire on something like a neuron, and then you do the backwards transformation to generate the desired equilibrium displacements for all the joints. Again, I can't go too much in details, but I will show you some experiments demonstrating that this concept works well for exciting the unknown dynamics of a variable compliance system. And this works even well when this variable compliance system is in contact with some unknown environment. So even in the hybrid case and of the ground contact impulses, you can easily excite by this concept nonlinear oscillations. We look today very much in the analysis, which has been done in our review paper on nonlinear modes and on a paper on strict nonlinear modes. But we invested in the last year also quite some time in how to stabilize and control those nonlinear modes. I will just refer here to the references because I don't have the time to go into details. And finally, I would like to show some simulations in which we exploited this bang-bang controller in some preliminary work to excite locomotion patterns for quadrupeds or biped robots. And we also apply the same concepts on some prototypical systems of a quadruped or a biped-like locomotion. And here you see that by this concept, we could implement a walking motion, then here a trotting motion, and finally, a bounding motion. Of course, I would be very interested to see if this concept of nonlinear modes is also good enough to provide hypotheses for explaining biological data from tracking measurements with animals. There are plenty of very interesting data of motion tracking and force plates of running and galloping and walking of different dog races. And it would be, of course, fantastic if we could bring back our knowledge from robotics to explain biological processes, because this reflects very well the way we perform robotics research in an attempt of understanding by recreating. We are looking at the biological model, use our engineering and biomechanics tools to try to understand the way biology works to build better robots, and then use the knowledge we generate in robotics to provide hypotheses and ways of designing experiments for biological systems. This is the end of my presentation. Thank you very much for your attention. Finally, I would like to end by introducing the next talk in this workshop. And this is the talk of An-Qui Lee from University of Washington. And the title is Safe and Efficient Robot Learning Using Riemannian Motion Policies. Enjoy.